Stefan. He specializes in computational mechanics and its applications. His work bridges gaps between engineering approaches and cutting-edge data-driven techniques. He's passionate about innovation, and his work has led to groundbreaking research projects, which obviously involve machine learning and physics modeling to solve really complicated problems. He is massively cited. He's an ISI highly cited researcher. He's been that way for about 7 years or so, supervised over 30 students, and he's written over 300 articles, and he's editor-in-chief of Advances in Applied Mechanics, and he's also a fellow of the Learner Society of Wales. What could be better than that? So over to you, Stefan, to deliver your lecture. Thanks very much.
Thank you very much, Omar. And in case you cannot hear me, let me know. Thanks a lot for the invitation to speak at Imperial College on this topic. So it's going to be about data and physics-centric engineering and healthcare. And in particular, this is related to the journal Data-Centric Engineering, which was founded a few years ago and in which we are part of. Okay, so there will be a few of these QR codes all throughout the talk, which you can follow in order to get to publication links or YouTube videos or other material that could be of interest to you if you are listening to the talk. You can also refer directly to our website, which is being renewed at the moment, our Twitter feed, as well as the YouTube channel, which is called Legato-team, which is the name of the team that I created in Luxembourg 10 years ago. And so today I'll talk about 3 ideas. One will be what are unknown unknowns and where it comes from, and try to link this to epistemology. The second will be human learning and machine learning, try to understand a bit how we learn, and maybe that will help us all see some of the difficulties we have with machine learning and some of the advantages and beautiful things we can do with it as well. So, and the third point is going to be about real-time model identification and parameter estimation for biomechanics, and also some points about digital and computational archaeology, which is a project that we started a few years ago. And this is the team I was talking about, so the Legato team. Legato because it links things up, and we have been working interdisciplinarily for almost forever. You can see that people are from many backgrounds. I was asked to count last time how many nationalities we had in the team, and I reached approximately 50, which means that that has been quite an international journey. Very difficult to pinpoint everybody on any slide, but this is the best I could do. All right, so let's start a bit about what brought us to solving the problems we're solving today. So this is a citation by Pierre-Simon Laplace, who is a philosopher, mathematician, and many other things at the same time. At this time, people were still able to do really many things. Today, things are much more specialized. And what he's saying basically here is that it would be possible if we could understand all moments and all forces and all the past and where it started, what the past went through until today. We could basically understand why we are at the point we are at today, and presumably also foresee what would happen in the future. And so that is basically what he's saying. He said that also in a different way, where he says, in order to try to understand uncertainty, that we are quite far from knowing all the agents of nature. And of course, if we were, then perhaps we would be able to predict things, as we often want to do as engineers and scientists. But instead, we have to be very careful, examine them with greater scrutiny, because usually we do not know what exactly happened, and we do not know things in a very precise way, and there is quite a number of uncertainties, and we will today see a number of cases where these uncertainties are important. And what he already said at this time is that when something is uncertain and we need probabilities, we also can figure out how many and what type of observations we would call that experiments, are necessary in order to obtain some sort of more certainty, or at least an idea of some sort of confidence interval that our quantity of interest is located within. And these are notions that we are quite familiar with as engineers, because we always know that factors of safety are a way to take into account uncertainties and probabilities about the state of the world. How much precipitation will you have? What will be the winds? What is the underground like when you build a building? And what are the material properties of the bridge that you're making out of concrete, for instance, or even steel? These things are all usually summed up and lumped into what we call factors of safety. So now we're going to try to look at how we move from factors of safety to a different approach to both engineering and also to healthcare. That's a big word, but at least to try to understand a bit how the body works and how we can intervene on this body in the best possible way as a surgeon. And so Donald Rumsfeld, much more recently than Laplace, said things that are going in similar directions, that certain things you know, others you don't know, and the difficult things are things that you don't know, because obviously they can lead to, let's say, disastrous decisions. And so why is it important to us as engineers? Because, well, the first thing is we do not know in which conditions the structures or the systems that we build will be operated in. So, of course, you see this Enterprise. You have no idea at all where this spacecraft is going to end up, and because you don't know, you need to take into account what you can in fact measure in reality. So, if you were to design such a spacecraft, which is supposed to go anywhere, without having any idea what this anywhere means, it will maybe be subject to radiations, to some huge temperatures or very low temperatures, to pressures, to velocities, to all sorts of conditions in which we could maybe not even predict a combination of, and we have to design and build these things in a way that makes sense so that they can survive during their service life. What is even more obvious to us as everyday citizens of the Earth is that the Earth is a one Earth system. It's only one system. It's a big system. It's convoluted. It has a lot of connections between ecosystems and industry and water cycles and food, agriculture, space, CO2 production, energy, and so on. All these things are interconnected, and you cannot look at one part without changing the other. So by making small modifications which look small, you can have an impact which is absolutely enormous on health or ecosystems and other parts of the system. So this is why we call these systems complex, because you can make small changes locally that can lead to big changes globally. And you can lead to emergence of phenomena that apparently are global, but in fact came from local exchanges of information at the smaller scale in the system. And we created a new doctoral program at the University of Luxembourg in complex system science. So I created it 5-6 years ago. It was then called computational sciences. Turned out that complex system science was much better adapted to the type of PhD theses that were defended there. So there are now about 70 students in the program, and we are looking at problems that range from social sciences, including happiness at the end of life, to archaeology, but also life sciences, biology, physics, and all sorts of parts of engineering. So these are the different parts of complex systems, and clearly these you recognize, such as pattern formations, nonlinear dynamics. In CFD, these things are very important, in particular in turbulence and so on. Game theory, networks, evolution, adaptation, and so on. So basically, we are looking at systems which are complex, meaning that they have one or more of these different components. And now when we look at those systems, we, at least in my group, and I think this is a large part of the research community, we look at it as a mathematical problem. So we start with a continuous problem, which is, for example, what we observe. So we would like to have an idea how the brain will deform if we apply a pressure on this brain applied by a needle, for instance, that needs to be inserted into the brain. And we then want to create a mathematical model of that continuous problem, which leads to a certain error, which is called a model error. So this is what I will call model error or model uncertainty. Model uncertainty is maybe more precise because model error would subsume that we have some sort of absolute model, which would be the optimal model. And that is an assumption which usually cannot really be made, because who is to say that a model is the best model? Especially when the quantity of interest hasn't been defined. So models depend on quantities that you're interested in. So let's call this error the model error. The second type of error that we're committing is the discretization error. Once we have a mathematical model, we discretize this model and we create a discrete problem. And this discrete problem is associated with an error level, and that error level depends on the type of discretization that you're using. For instance, if you're interested in fracture problems that propagate during the life of a system, then these fractures will lead to local stress gradients, so very localized solutions close to the crack tip, similar in fluid dynamics to turbulence. And these nonlinearities will need to be taken into account, and they lead to even worse than nonlinearities, they lead to singularities. And these singularities, in certain cases, are very difficult to take care of using standard finite elements, or standard numerical methods. So people resort to, let's call them advanced numerical techniques. And those techniques allow to decrease the discretization error in a better way, let's say more efficient way than simply using standard techniques. And those include enrichment schemes or certain mesh methods, isogeometric methods, depending on what type of error you're trying to target. And once you have the discrete solution, you solve it numerically, so you add a numerical error to the mix. So during the whole talk, I'll be talking about validation as the measure of model error or model uncertainty, and verification as the measure of discretization error, which ask two questions which are quite different. Validation answers the question, are we solving the right problem? And verification, are we solving the problem right? Once we have assumed that the problem we started with is indeed the right one. Most of the time, of course, we do not know the exact solution. And some of the work that we've done, in particular in fracture mechanics, but also in biomechanics, is to introduce real-time error estimates, which are able to tell the user, assuming that the model is the correct model, how accurate the solution is locally in real time. So we are able to, in real time, assess the discretization error for problems involving fracture, propagation of fronts, needle insertion, and fracture mechanics. So those are a few of the examples. So now I will go back a step now, leaving engineering for a little while, and going a bit into cognitive science and psychology to try to see how we learn and trying to make a link with how machines learn. So all the discussions that I do now until the next part of the talk is going to be based on the work of Stanislas Dehaene at Collège de France and in Paris, who focuses on trying to understand how we learn. So how babies learn and how infants learn, and how young toddlers and children learn. So I'm going to start by defining a few points. So for example, let's assume that you are watching a talk, a science talk, for instance, maybe the talk I'm giving at the moment. So you have, before you came to this talk, either you knew me, or you knew my work, or you were curious about it, and you had a hypothesis in your mind. So you said, oh, he's going to talk about something related to data and machine learning. I have some interest in that, so I have some free time. Let me go and see how it is. Or maybe you knew me very well before because you worked with me in the past, or you worked with someone who worked with me and you heard this guy gives talks of that type and I'm interested in this, so I have a hypothesis on that. And then what's going to happen is that during this talk, I'm going to give you evidence of whether or not what you thought is true or not. If you had no prior information, no knowledge about the talks that I usually give, this evidence will be the only knowledge that you have. Let's say that you have no knowledge about what my team is working on, for example. And during the talk, what you're going to build is you're going to knock the hypotheses with the evidence, and you're going to get some sort of what we call likelihood. And that likelihood is going to answer the question, how probable are my observations given my initial hypothesis? So this is a bit complex to understand at first, because one thinks of observations as what we see. So saying that observations are probable sounds counterintuitive because they are what they are in front of you. So how can something that is be probable or improbable? So what we are saying here is that there is some sort of cognitive or machine learning, or we will give it different names later, phenomena that take place which allow you to compare your observations with the initial hypothesis. So let's see how it works in practice. Once you have this new likelihood, that will become the new knowledge, right? So let's say that a year from now I give another talk, you will have seen this talk, and now you have prior knowledge. So your prior knowledge, which was, let's say, nothing, becomes enriched by your experience of this talk and becomes the new prior, which is called posterior. And this posterior is what you now know about the talks that I give. And you will maybe watch a second talk next year and you will update your evidence. Maybe my second talk is totally different from the first, or maybe there is something that reinforces your learning and reinforces what you actually thought you knew about the talks that I give. And then you will build a new likelihood function. And again, you will ask the question, how probable are my observations given my initial hypothesis? Am I surprised by this talk, or is it a talk that I was expecting because of the types of talks that I saw from the speaker before? Another way to think about it is to think about playing tennis. So for example, if you play tennis with someone you may know that they serve always in that corner. Or let's say there is a high probability that they do. Then you watch the person actually moving their body around, and you watch the angle of the racket, and that actually confuses you slightly because it seems to be indicating that the serve will go more towards the right-hand side. And so what you do practically is you confront your initial view to what you see at the moment, and you try to predict what is the probable position of the serve, which is the intersection between these two. And if you write that in terms of jargon, you say that you have prior knowledge, you confront it to the likelihood, and that gives you a posterior distribution. And this is nothing else but the law of conjunct probability, which we all learned very long time ago, which gives you the probability of some event knowing another event. So probability of what you observe knowing what you know. And this is exactly what Stanislas Dehaene and others, in that case one of his colleagues, has observed in real life. So let's assume that that someone is looking at this bowl, this sort of chamber. And in this chamber you have different objects. And first you see them moving around, and then someone puts a veil in front of that chamber, which means that you don't see them moving around anymore. All right? But now one of the objects comes out, and the idea is to try to figure out whether the subject watching this is able to predict the probability that this type of object comes out as opposed to the other type, which is clearly less numerous in the box. And so now you have two cases. One is improbable. In the left-hand side, of course, this object that comes out is less numerous than the others. So statistically speaking, you don't expect it to come out because there are fewer of it in the box at the beginning. Whereas in the right-hand side case, you of course expect this object to come out because it's more numerous. And what was shown by Teglas is that kids at already 12 months, which is quite early, are already surprised by the left-hand side case. So if they are shown this case and this thing comes out, then they are completely surprised. And the way you see it, you can follow the paper there, is that the face of the baby or infant is actually showing. So you can measure that really scientifically by looking at the pupil dilation, the way the eyes are moving and so on. There are ways to show that the baby is surprised. So that means that babies at age 12 months already have some notion of probability because they can be surprised when something improbable happens. Another way that the brain can, in that case, deceive us is about writing. You probably noticed, whether you have children or you met children or you taught children to write, that at least in the type of alphabet that we are using in Western Europe, we have letters that look very similar. So for example, D and B are very similar, and Q and P and so on. So when kids learn to write, you notice that they tend to reverse letters. They tend to write them in as mirror images of each other, a bit like in this picture. You have the portrait here, and you have the left and right hand side views, and it seems like babies are actually confusing these things. And the question is, can we understand why this is happening, and how is that helping us understand how people learn? So if you show a kid, and not all of them do it in the same way, but if you show a child the word Odile and Libo, they will think of it as potentially the same. And the reason for that is that the brain learned over generations and generations to recognize faces, because this is a very important trait in evolution. And to recognize faces, you need to make sure that that face on the right is the same as the one on the left, because faces tend to be rather symmetric. At least it's not very easy to find lacks of symmetry by visual inspection. And so if you look at the right-hand side and left-hand side, the brain must think that these are the same things, because indeed they represent the same person. So now for words, because of this pre-learned aspect of the neural connections that are made in the brains when you actually see something symmetric, you tend to think that everything else is also mirror imaged. So when you learn to write, which is something that is not ingrained in the brain for as long as recognizing faces, because we invented writing much after that, we have to unlearn that everything is a mirror image of each other in order to learn how to write. So this is a bias which is built inside the learning and which is reinforced by the fact that we have learned over generations to think that everything is a mirror image of its own. So if we summarize that part, we can say, as Gopnik did, who was a psychologist, she said that the baby is a scientist in the crib. From that point of view, one can think that babies draw conclusions from hypotheses, so they formulate hypotheses about the world, and then they confront that hypothesis to what they see. And this is what in our field we call Bayesian learning, where we enrich prior information with experience in order to build what we call posterior information, and that posterior becomes the new prior, and iteratively we build a vision and an image of the world around us. And essentially, whenever we talk about a model, which is a word which is overused and used left, right, and center with completely different visions of what it means. For biologists, a model of humans is a mouse, for example. When we use a model, we do exactly that. We have some sort of abstract representation of the world around us, and we try to use that in order to describe this world and to then try to interrogate this model to make predictions or to look at optimization or to try to see consequences of changes in the parameters of that model. And so, of course, this is what we do continuously. And based on the plausibility of what we see, the hypotheses that we made are more or less plausible, right? Given the evidence, our hypotheses are more or less plausible. And this is how we refine our knowledge. What is very important also to imagine is that in the brain, which is something I was fascinated about when I listened to the lectures of Stanislas Dehaene, which are all recorded and available online, by the way, very interesting, as well as his books, The Baby Statisticians and How We Learn. The signals in the brain are uncertainty signals or error signals, which means that this is actually how we learn. And everybody will agree, I guess, that the school system is quite unaware of the fact that making errors is teaching us something, because they tend to actually penalize errors by giving negative marks. So it's not to say that we should, let's say, reinforce errors when they occur, but the idea is to actually get rid of the negative aspects associated with errors. So let people learn by making mistakes and allowing them to figure out from the mistake how they can get better. And this is exactly what we do in machine learning when we do reward learning and so on. So if all these facts are indeed facts and are true, then our brain may be working in a Bayesian way. And in fact, some researchers are now trying to come up with approaches to mimic the human brain in order to make Bayesian simulations faster, which is quite exciting. And so it's important to us as modelers and as engineers, because in practice, the data-driven modeling approach, which we all talk about, is concerned with finding a mapping between an input and an output. This is the function f, which we are looking for. This is the model. We either assume it or we look for it. And today I'll talk about cases where we either look for the model or we assume a model, and we verify or validate rather whether that model is correct or not and how correct it is, depending on the quantity that we're interested in. And then we have two extreme cases. In the first case, the structure of f is known, but the parameters are not known. For instance, you may know something is linear elastic, but you don't know the stiffness. Or you may know a fluid is non-Newtonian, but you don't know, let's say, the viscosity, for example. So you know the structure, but you don't know the parameters. The other extreme is when you have absolutely no a priori knowledge about function f. So that could be, for instance, what happens in the brain of a flatworm. You have neural connections, but you don't know how these neural connections work, and you are not going to model them individually using mechanistic approaches. And usually where we are is somewhere in between. So we are between the Newton case, where you have some sort of hypothesis about how the structure of the model works. So F equals ma, acceleration of gravity is universal, or the opposite case, let's say a Twitter network of collaborators or connections, which looks totally messy and which, until now at least, there is no analytical form that is going to tell you the number of connections of any given person given some sort of analytical formula. So this is all based on data and data only. And most of the interesting bits are between the two extremes, in my opinion. So where you have neither small data or big data. So when you have uncertainties, but you do not have sufficient data to get rid of the uncertainty completely, but you also have some knowledge about what you expect of the system, what people call in that field physics-informed approaches, which were talked about in previous seminars of the same type as this one. So now what we're trying to do is we're trying to discover a model. When I say discover a model, I don't mean necessarily the functional form, but also the parameters that go inside that functional form. We're trying to discover that based on observations which come from the right-hand side, data, in other words. So that is what we are interested in my group very much. And now let's think of machine learning and see, of course, not in detail what machine learning is, because it's so complex and so varied that it's impossible to summarize. in a short time, but let's take a very simple case and see how it relates to what we just talked about. So these points are extremely simple in machine learning. What you are trying to do, at least in some parts, again, of machine learning, is to regress. So you're trying to start with a bunch of stars, which are in a coordinate system that I drew here, and you're trying to find a line which is going to fit these points in the best way possible according to a certain norm. So you're going to define what the norm is, let's say L2, so sum of the squares of the distances, and then you're going to say, okay, well, now I want to find this line, so what is the intercept and what is the angle, what is the slope, in order to minimize the loss. So that would be a way to minimize what's called the loss function. And the loss function is nothing else but the difference between the target, which is what you want, and the prediction, which is what you predict. So the target is, let's say, what you see, and the machine learning prediction is what you predict. So it's your internal model. So your internal model minus what you observe should be as small as possible. And that's what we do in all fields of engineering. And this is the way it works in neural networks, at least in one type of neural networks, is that you have a forward propagation where you assume a model. In that case, it's some linear model. And then you have some sort of blending function that have different names, activation functions in that case, which perform some nonlinear combinations. And then you do that layer by layer until you make a prediction. And this thing is the combination of all these functions weighted by these coefficients. And at the end of the day, what you do is you try to do what's called backward propagation. Once you have the function, you minimize the functional with respect to the parameters. And that gives you an idea about how the system behaves. So it's like some super approximation function, exactly as people develop moving least squares or generalized collocation approaches and generalized approximation schemes. These are exactly the same ideas. You're trying to fit a function with more fancy and more difficult to interpret approximation schemes. So this is the idea. So in our group, what we did is, this is the thesis of Saurabh Deshpande, who defended a few weeks ago. And he was interested in large deformations of soft tissue like rubber or hydrogels and the like. And in that case, what he was really interested in is trying to do a few pre-computations and use those pre-computations to train a numerical model, in that case, a neural network, in order to make fast predictions. So the idea is a bit like in reduced order modeling. You want to replace the model by a surrogate, which means something which replaces the basic model, which is very, very expensive to compute. You want to replace this model with a surrogate, which is much faster to compute, in order to make real-time online simulations. And this is useful for us because we work with surgeons that try to treat people, and these surgeons have to do certain operations very fast, and they need to know what the deformation of the body will be in order to know what to do in real time. So for example, they need to predict the deformation of a tumor, but of course the problem is that they do not know the stiffness of that individual in advance. So the idea is that you do some pre-computations and you then use data in real time to fit the model better to reality. But in that case, the interest was different. The interest was simply to say, I will make some pre-computations so that online I can make 50 calculations per second. And it doesn't matter how many pre-computations I had to do in order for that to happen. And this was the idea here. And so Saurabh developed 3 different methods based on convolutional neural networks first, which is very practical because we start with MRI, which are all based on voxels, which have the same data structure as convolutional neural nets. The second was a so-called magnet approach, which is a graph approach. And on top of that, he worked a lot on trying to extend these neural networks to Bayesian approaches in order to allow the network to extrapolate. Because one of the key difficulties in this type of approximation is, well, first, that the neural network doesn't know anything about the physics. Of course, there are ways around that that other people are focusing on. But there are also ways to give bounds to the solution. So the problem with these methods is that as long as you stay in the interpolation range, meaning that the deformations that you are looking at, for example, stay within the training regime, everything is fine. But if you look at deformations which were not part of the training set, then you see immediate divergence. And the problem now that Saurabh was trying to address is, can you give estimates of the let us say confidence interval in which the deformation is? So can you say that the deformation is 2 millimeters plus or minus 0.1, and that you are 95% sure, given the knowledge you have on parameters, that this will be the case? So this is the work that Saurabh did, which is in his PhD thesis. Okay, and this is all based on the attention mechanism. Okay, now we'll take a small break because it's, let's say, middle of the discussion, maybe a bit more. And in order to show you the importance of attention, this is also what is in the ChatGPT approach and what is in Saurabh's new neural network approach. And so I'll ask you to focus a bit and to try to count how many times the players that wear white pass the basketball to each other.
White pass the basketball. How many passes did you count?
So I let you.
The correct answer is 15 passes. But did you see the gorilla?
Okay, so that little game was there to reinforce the importance of attention. An attention mechanism in neural networks is absolutely critical, and if you use ChatGPT, you can already realize that there are some issues that are related to the fact that the attention of the neural network is limited to a certain number of words or characters. And so in that case, of course, that's how I worked on. The problem is exactly the same. So now let's see how we got to where we are in order to introduce the two case studies, I hope, that I'm going to talk about. So first of all, I'd like to tell you where I started. So my PhD was in 2003, and I'll be brief about this. And I was working on numerical methods for aerospace, where we were looking at fracture propagation in cast aluminum structures for aerospace. And all that was linear elastic and based on Paris law. So everything was essentially semi-empirical laws that had been devised decades before, and that on average knew about the way that metals behaved. So for example, aluminum and so on, that had been tabulated. So you knew that if you apply a certain load, that creates a stress intensity factor that you can compute. And based on that stress intensity factor, at each step of the loading, you can predict how much the cracks will propagate. But this is all pre-tabulated based on the knowledge of the type of aluminum that you have and how it was built and how it was manufactured. After that, I started moving to very much more realistic cases of landslides and nonlinear fracture, where the types of approximations of the model now were completely different. So instead of having tabulated approaches like Paris law, now we wanted to locally measure a new technique to, in fact, predict the propagation of the crack. So this is what you see here. We are taking into account the actual microstructure of the material to decide, let's say, in which direction the crack will propagate. And this is possible because you have, again, now some data about the material. You need to know what grain size will be there, how many grains of certain size will be distributed, and how in the domain, where the grains are, and so on. And then if you know that, you can devise methods. It's quite complex and extremely computationally demanding, but you can take into account the microstructure in the propagation of cracks. And after that, I somehow randomly met a neurosurgeon, and this neurosurgeon told me that they had difficulties simulating and predicting in their brain. So, internally simulating the deformation of the brain when they were operating, and therefore it made their life difficult in order to reach a given target. So since the neurosurgeon was talking to me about resection, meaning cutting away some tissue, and I made the link, which is quite trivial and simplified, with fracture, I thought, okay, maybe we can do something. And the first question that I asked myself is, can we solve cutting in real time? And we were able to do that in about 2004 with Adrien Courtecuisse. And after that, we started thinking about how accurate are the solutions, which is something in computer graphics which is never done. So in real-time simulations, very few people are concerned with the idea of how accurate the solutions are. They need to look good, but if they are not very precise, mechanically speaking, usually that is vastly ignored. So we were able to take care of that. And after that, I realized that this was far insufficient, because as much as it allowed us to answer the question, are we solving the problem right, meaning is the solution to the problem accurate, knowing the problem, it did not help us at all in understanding whether the model itself made sense, whether we needed a hyperelastic model or a hyperviscoelastic model, a poroelastic model, and so on. And so this is what I embarked upon, although I had sworn in the ERC grant that funded this work that I would never do it. I started working on computational constitutive models because I wanted to know what was the impact of variations in certain parameters on the quantity of interest, which was the target motion. And then I realized that the problem that I would always have is that I would never have enough data in order to figure out what probability distributions would be for each parameter of the model that I needed. For example, in certain hyperelastic models, you have up to 5-7 parameters, and all these parameters are difficult to model. You need a lot of experimental data to be able to have some sort of level of certainty about what they mean. And what I mean by that, I mean having a distribution of each parameter in terms of either Gaussian or Weibull or whatever it is that you have. Having such distributions needs a lot of data, and unfortunately, we have absolutely almost no data. And on top of that, we have certainly no data on the patient that is going to be operated today, because we never measured the properties of their brain. So that led us to start thinking about how to update models in real time without knowing a priori what the material parameters would be like. So we asked ourselves the question, okay, what type of model can we start with that are simple enough but not too simple, in order for us to be able to identify the parameters fast enough during the intervention or during the work of the surgeon or medic, so that they can they can work properly. And so there are many other topics that we worked on, and today I can only touch upon a few of them. But I selected them so that they give an idea as to how we have been coming to that case, to that situation today, because I think it's always quite insightful to think about how we got to the stage we are at. So the first thing I'm going to talk about is astrocytes. So astrocytes are cells in the brain. And so this is our first case study. This was the work of Sofia Farina. And you see here two types of astrocytes. On the left-hand side, this is a healthy one, and on the right-hand side, this is a diseased one associated with Alzheimer's disease. And now the question that Sofia was working on is how important is the shape of that astrocyte, the morphology. The animation you see is an astrocyte from a mouse, on neural metabolism. So why is it even related? So what are these astrocytes and why is it important? So astrocytes are, first of all, the most abundant cell in the brain. They take their names from the star shape that they have, and they connect the blood vessels that you see there to the neurons. And the way they connect them is that they take nutrients from the bloodstream give it to the neurons, and vice versa. They take garbage, let's say, garbage collection from the neurons and send that back to the bloodstream, among other things. But now let's focus on that point. So they are metabolic mediator, and they provide neurons with lactate, which is a way to essentially pass energy along so that the neurons can work. So the hypothesis would be, if the neurons are starved of energy, they may start to degenerate, and this may lead to Alzheimer's disease. This was an assumption. And the question that Sophia was trying to answer, it was, okay, this is a healthy case. Is it related to the shape? Is the passing of lactate efficiently related to the shape? And if so, how? Because if it is related, maybe the fact that this Alzheimer's diseased astrocyte has this shape has an impact on metabolic actions in the neuron. So this was what she was working on. And in that case, the data that was there was simply 2 MRIs of the 2 small astrocytes. And that's it. Two images of the 2 astrocytes, one deceased, the other not deceased. And the reactions that she was modeling are diffusion reactions that you can see here, which are quite common, with a certain number of chemical reactions taking place. And what the first output of her PhD was a full simulation of a non-reactive, let's call it astrocyte, and a reactive astrocyte. And then the consequence of that simulation was to say, the conclusion is that there is a huge impact of the shape on the way that lactate is transferred to the neuron. But as you can see, the model is super simple. There is, insofar as there is only one astrocyte model, and it's one particular astrocyte. And of course, the question would be, how does that translate to other cases? Then she worked on calcium dynamics, but that I will have to skip in order to make it on time. So I will now go to the second case study, which follows up directly from what I was talking about in the introduction to this data-driven approach. So Arnaud Mazier, during his PhD, has been working on this problem here, which is to try to merge data from what you acquire in real time. So here the idea was, it was a European Investment Bank. So Arnaud was scanning this person here, who is a worker at the European Investment Bank, one of the economists, and in real time he could get the shape of this banker, and unfortunately, the question was, of course, that the shape of a banker is not really helpful from a medical point of view, but this is only to show you how these things work in practice. So what we were doing then is to say, okay, what can we do in order to help people that work on breast conserving surgical pipelines? So the first question is, what is the problem? So we have pre-operative imaging. So we see here a patient that's lying on the belly, and the breasts are being imaged. And the idea is to try to figure out where the tumor is, and then to apply some sort of mapping in order to know what will happen during the surgery. Because during the surgery, the patient is not lying on the front, but lying on the back. And therefore, the tumor that was located here needs to be fit in order to be deformed and get to a given situation in the actual surgical case, as you can see here. So the tumor is localized somewhere, and the idea is, how can we compute the deformation from this lying on the front position to the lying on the back position? So for that, the idea is the following. You need to have a model, of course, of the breast, because you will not have enough data during surgery to be able to get rid of the model completely. So you're really in the sweet spot between the data only on the right-hand side and the PDE only on the left-hand side. And the idea is the following, that first of all, you need to get rid of gravity in order to apply it on the other direction, right? Because the breasts are initially loaded by gravity in the vertical direction, aiming down. And then when you rotate the patient, this is equivalent to actually rotating gravity, unless you take into account contact, which for now let's forget. So the idea was, okay, you take virtually the patient to the space station and you remove gravity, and then you apply gravity in the opposite direction or in whichever direction you need in order to take into account your real position. The difficulty here is we assumed a very simplistic material model, but we still don't have the parameters, and we don't know even the boundary conditions very precisely. As I was saying, contact is a difficult case here. So first, we need to compute the inverse deformation. And once we've done that, we start from the application of gravity towards the interior. Then we estimate the deformation in the supine, meaning on the back situation. And then we go and we essentially iterate, right? So we compute the mean absolute value of the error, and then we iterate until we get the optimal configuration, which is what we see using the scanning technique that I was showing in the European Investment Bank. So now the idea is we basically compare two positions, and in order to do that, we just do a minimization, but this has to be done in a real time. And of course, for that, having surrogate models and acceleration, such as the work of Saurabh Deshpande that I showed before on surrogate modeling using AI and machine learning, is exactly what you need. And so if you want to see that in action, so you see here the iterative process where you see the targets that are trying to be matched. And that matching process takes a few seconds. So it's not exactly in real time in the sense that you cannot see it live on the screen at a refresh rate of 50 hertz, but Arno managed to do that very, very efficiently and very fast. And what is very useful, I think, also to think about is that all these biomechanics simulations are usually quite complex. They have to rely on material models that have, as I was saying before, up to 7-8 parameters. And there is a lot of know-how in how to implement these things. So what Arno did with the team of Stéphane Cotin at INRIA is to merge two pieces of software which are quite different from each other. Phoenix, which you may know, which is related to solving PDEs in parallel and directly from the strong form. So very mathematical piece of software, highly optimized and able to run in parallel natively. With SOFA, which is basically originally computer graphics approach, where you try to simulate very fast at the expense of accuracy. And so in Sonics, what SOFA and Phoenix can do together is that you can use SOFA in order to be in real time, and you can also use Phoenix to derive all the partial derivatives that you need and the linearizations that you need in order to compute a linearized problem. So you linearize using Phoenix, the code is written and transferred to SOFA, and all that is running smoothly in one seamless conjunction. And what is very interesting for me at least is that you can change the material model by changing only one line of code. So if you change the material model from Ogden-Holzapfel to Neo-Hookean, or from Neo-Hookean to Ghent model, for example, that can be done in one line of code, which I think is quite remarkable. Okay, so here you see the haptic device that's used in order to, in real time, probe the lever and get the deformation that you need. So Arno is operating it here, and the lever is deforming in real time during this. And what we also added is error control, because as I was saying before, usually we have no idea about the error level, and this is a problem in biomechanics because there are huge numbers of uncertainties. We are already quite uncertain about the model, and at least I have always been an advocate of trying to minimize the discretization error as much as possible in order also to let the mesh be optimized for the quantity of interest. Because what you see on that slide, which is to me super interesting, is that depending on the quantity of interest, the mesh that you get is totally different. So if you're interested in the pressure, the mesh that you will get is totally different than if you're interested in the displacement field, for instance. And this is something which is rarely talked about, especially in biomechanics, and which I think could significantly simplify the meshes and the simulations, and also improve the robustness and the certainty and the confidence that we have in our simulations. Okay, so now I'll move to the second case study, which will be a bit shorter than this. Well, it's the third one actually. And we are completely switching gears. It's an archaeological digital forensics project where the idea is the following. It's in Tel Nebi Yunus, which means the hill of the prophet Yonah, which is in Mosul in Iraq. And it's very historically important site because of some very long cultural continuity and many, many different religions and civilizations succeeded to one another in that area. Okay, so underneath that hill there is an Assyrian palace which was discovered, and before that was discovered there were different edifices on the top. So early Christian monastery, after that an Ottoman mausoleum, then Saddam Hussein did some remodeling of that mausoleum. Then the Islamic State did some more permanent remodeling by destroying this mausoleum and looted the place in order to get some artifacts to sell on the black market from the Assyrian palace. So what Juan Aguilar, who is our PhD student founded by our Institute of Advanced Studies, which was created at the University of Luxembourg by Jens Kreisel when he was vice rector for research, is the following idea, is that he took digital photogrammetry of the walls, so similar to the method used before by Arnaud for surgery. Now he did that in real life, let's say, in an actual archaeological site. He scanned everything from the surface to the tunnels, and try to scan all the architectural features that he could. And then he georeferenced everything, as well as the tilted floors, slanted floors, walls, broken stone panels, and the cracks, and so on. And then from there, try to answer the question, when was the monastery first built? Because these questions are not obvious. For how long was the palace exposed to the load coming from the monastery? Only knowing the deformation in the present. So this is, as you can imagine, very difficult because it's an inverse problem. You know only what you see today, but have no clue what went on in the past, and you have uncertainties everywhere, including in the soil, in the material properties of the mud bricks that were used, of the timber that was used as well, because we think that they were using trees that were coming from Lebanon, that were up to 40-meter long, but of course that is difficult to verify. So all these questions need to be answered, and computational methods can help do that because we at least can look at different scenarios. And we can then learn from the scenarios what is actually likely to have taken place. And in parallel to that, do actual measurements on site in order to confirm or infirm these measurements. So you can see here that we have a first huge difficulty, which is that the point cloud has billions of points, literally. And as much as one can solve problems with billions of unknowns, in order to solve an inverse problem, you will need to do that so many times, like hundreds of thousands of times. And this is clearly not something feasible and not desirable also because it's quite brute force. So what we would like to do is, again, similar to the mesh optimization before in biomechanics, we would like to optimize the point cloud such that the important features are retained and the non-important features are not retained. This is also very important in industrial engineering, where you have assets like any sort of industrial assets that you want to look at and to maintain over time. If you do that regularly, you will have point clouds taken by drones, and your question is, what changed between last observation and today's observations? And in order to do that using point clouds only, this is very difficult because you need to take into account the point clouds, and this is very tricky with billions of points. So you would like to be able to simplify that. And that is what we have been working on. As a first case study, we looked at our building, which is a 19-story building here in Belval in south of Luxembourg, in order to do a fire simulation. So we wanted to see what would happen in case a fire takes place somewhere in the building, because there was a fire evacuation, and it turned out that people had opened the vents at the top of the staircase, which acted like a chimney. And in order to explain this to people that are managing the building and try to avoid that they do that next time, we did a simulation in order to show what would happen both to the smoke if the vents are open and to the fire. So as you can see, the smoke, when the vents are open, very quickly rise to the top. This is the principle of a chimney with a negative pressure at the top. And the smoke, in case the vents are closed, of course, stays contained within the first meters above the fire. And we did that using full 3D photogrammetry of the place, which we did, Juan did with our postdoc Pratik. And then based on that, we did some simplified SPH simulations of the fire. And that's it. So I will skip case study 4 because we do not have the time to do it now. I'm sorry about that. I would very gladly talk about it another day. And I will thank you for your attention and would be very happy to answer any questions that you may have.
Stefan. Great. Stefan, that was a real tour de force. Thanks very much for that. That was really quite amazing. I can now see why you're so highly cited. You know, you solve a bunch of different problems using similar techniques, but in a wide range of settings and applications. And you seem to be making an all-to-one contribution across all of them. I think that's terrific. I actually have to go to another meeting, but I'm really desperate to ask you one question, which is, can you see through your experience so far, whether there's a class of problems for which we need to develop a new set of tools or a new set of techniques, or maybe a unique combination of existing ones?
Yes. That's very very tough question. That I wish I could answer it, because probably it would allow us to make much faster progress. I think it is the question, really. So let's see. I mean, I need to think in real time now, which is much harder than to compute in real time. So, I mean, from my point of view, if the problem is the data acquisition probably point, because if we can acquire data sufficiently fast, then we may not need a model, and vice versa. If we know very much how the problem works, then we don't need the data. So my sort of gut feeling would be that the worst case is when we are both on a mediate, on the bisector, basically, where we are exactly in between, where, we have neither too much data or too much knowledge. And this is, to me, the cases where it's the hardest, which is sort of, I don't know, maybe the obvious answer. I don't know. I didn't think about it in this way, actually. Thanks for asking. No
problem. That's completely fine. I will leave you in the capable hands of Nashim, but I've got to jet off to another meeting, which started at 2:00. But Stefan, you have an open invitation to come and visit us anytime you like. I think it would be great to work with you, in fact, and congratulations on all the stuff that you're doing, to you and your group as well. Okay.
Thank you very much. I really appreciate it, and I'll be sure to take it up.
All right.
Actually, I have a PhD Vive at Imperial soon, so.
Okay, yeah, come and knock on the door. I think it'd be great. All right, cheers.
All right, see you, Mark. Right, I can't see any questions on the chat. I'm not sure if anyone wants to unmute and ask a question. Hi, Huang. Are you planning to ask a question? Go ahead, sorry.
So now, this I can say good morning, Stefan. I didn't see you very long time.
Yes, thanks for connecting.
Yeah, right. This is because I got the email maybe yesterday, maybe. Yeah, exactly yesterday. but now I also invite my student, Mr. Kim, and other student also join together here.
Thank you so much.
Actually very interesting talk, because I didn't see your talk because I also last time I attend your talk in Belgium, and after that we had very long time I didn't see you here.
Yes.
And now I really want to ask you about the machine learning, because in machine learning, especially for very complicated problem like your model.
Yes.
Normally, when we solving with the loss function, and actually some case, of course, we okay, for bit data, we compute and how we can optimize the loss function, and in the case we get the very small error, we say that the solution is good, but we don't measure that, because this is I mean that this is the overall error, okay? But
Yes.
But it for maybe I mean the local error, like because in finite matter we make a refinement adaptive refinement in order to reduce local error, right? But so and recently I learned
okay.
about recently I learned about explainable AI. Because explainable AI, that means can concern about the local error, because normally when we get a very small error, but about this is overall error, total errors. But actually we don't know how about the error as the local level, because in some case, even some case very sensitive, the local error even is large enough, but the error, the machine learning cannot get very well solution in a real case.
Yes.
So I mean, I focus on uncertainty of the output of solution using machine learning. So do you know some case that's because we are working on areas, but we don't measure how machine learning can do very well all case, especially for complicated problem. This is also facing with many bad situation in the solution.
Yes. So if I understand correctly, I'll try to rephrase the question to make sure I understand. So you're asking if you look at the neural network like a set of points, you can imagine those points like some sort of finite element node, and in finite elements you would refine the mesh locally because you would add some points, but in neural network what you do is you only get the global solution and you don't know what happens locally inside the neural network. Is that what you're asking?
So I mean I refer the uncertainty of the output solution.
Yes.
Even the at the global error. Okay.
Yes.
Even we earn small enough the errors, but at a local error, because what happened between the error between exact solution and approximate solution, but on the omega domain, but we have just one point, very large the error, but another point, a very small error, we can omit everything. We just concern only one point in the local. This is even totally over. We also get a small error enough, but actually the error at the local where effect very large of the output is very important. This is I mean I focus on uncertainty of the outputs.
Yeah, absolutely.
Yeah, right.
I mean,
Right.
I totally understand what you're saying, and I think it's a very important question. I've not looked into it a lot. The only thing we've done with Saurab is to give the weights some sort of uncertainty, you know. So in that case, all the connections between the neurons now are not certain but uncertain, and we try to take that into account in the output. But we don't. We haven't looked at explainable AI yet. But clearly this is something we want to do. And the other thing we would like to do is also to try to see if the connections between the nodes could be maybe made to be physical, so that you could have some physical interpretation of the connections, so that you cannot spit out any possible output, but an output which is constrained by the physics. So a bit like pins, but except that this is not done using a collocation approach, but more where the weights between the different nodes are taken into account as physics-based, let's say. But I don't know anything at the moment about it. I've not looked at it yet. However, I think that is also one of the questions to think about.
Yeah. Okay. Thanks, Stefan. Thanks, Boras.